We live in an age when it seems as though there are no unanswered questions, no mysteries left to solve. Yet as humanity's technological achievements grow ever more impressive, we find ourselves confronted by an astonishing realization. We may have been wrong about everything. And broadcaster Carlo Rovelli lays out a compelling case for why time, as we experience it, is probably an illusion. The key to understanding, he says, lies in taking a journey into the tiniest realms of reality. As the 20th century wore on, scientists struggled to reconcile these two frameworks. They managed to achieve remarkable successes, particularly in understanding the microscopic. His research illuminated a deeper meaning behind the Wheeler-DeWitt equation. It turned out the equation was saying something profound. The absence of time in this equation doesn't just reflect the quirks of maths. It suggests that time, at its most fundamental level, might not exist, but the evidence is tantalizing. If time turns out to be just a story our brains tell us, what does that mean for the nature of reality? We've tried to measure it, predict it, and understand it. But maybe it's time to rethink what we think we know about time. Maybe it's not a tick-tock on the clock, but a story in our heads that drives our experience of the world. Whether or not that's true, one thing is certain: our exploration of time and the universe is far from over. Who knows what other mysteries lie hidden in the depths of reality, waiting for us to uncover them? The world may never cease to amaze. Does it mean that nothing is real? Not really. It just means that reality is more complex than we thought. Please subscribe for more videos. Thanks for watching. It suggests that our brains have evolved to make sense of the world by constructing stories based on patterns. Stories like time, like cause and effect, like space. These stories help us navigate the world, but they're just that, stories. The deeper reality may be beyond our comprehension, but it won't stop us from trying to understand it. That's right. Time, as we understand it, might just be an illusion. But the dream of a single framework that could explain the behavior of the entire universe remained elusive. After all, we clearly experience the passage of time. It's an emergent property, a story that arises from the patterns in the data collected by our senses. So what about the arrow of time, the directionality that makes time seem to pass in only one way? The answer to that, according to many physicists, lies in thermodynamics. Thermodynamics deals with how energy transforms in physical systems. The second law of thermodynamics introduces the concept of entropy, a measure of disorder in a system. This law states that the entropy of a closed system always increases over time. Hot objects cool down, eggs break, sandcastles erode. The second law paints time as a one-way street, moving inevitably towards greater disorder. But what's fascinating is that this law seems to be a consequence of our brain's pattern-making abilities. Our brains are biased to find order in chaos. We see faces in clouds, stories in random scratches on a wall. It's this innate drive to impose order that gives rise to our perception of the arrow of time. It's not a fundamental aspect of reality, but a story our brains tell us about the patterns they detect in the world. Days turn into years, seasons change. Time seems as real as anything we know. The answer, according to Rovelli and others, lies in the way our brains process information. Our brains are, in essence, pattern recognition machines. We evolved to perceive patterns in the data our senses collect about the world. And time, it seems, is just one such pattern. Consider a computer simulation of the universe. A simulation is, in essence, a series of still images displayed in rapid succession. Each frame is a snapshot of the system at a particular point in time. Now, if you were to look at these images individually, you wouldn't see anything meaningful. You'd just see a series of static pictures, but put them together in the right sequence and you see a movie, a story unfolding over time. The illusion of time's passage is created by our brains imposing order on a sequence of static images. It's a similar story with our experience of time. Our brains are designed to extract meaning from the world by identifying patterns. And it seems that our perception of time is just one of these patterns. We interpret certain physical phenomena, like the changing seasons or the movement of celestial bodies, as signs of time passing. But at the deepest level, it's just a story our brains tell us about the patterns they're detecting. One of the most baffling aspects of this conundrum was the conflicting views of time. According to general relativity, time was intertwined with the fabric of space, forming a four-dimensional continuum known as space-time. This meant that time wasn't absolute. It could stretch and contract under the influence of gravity. Near a black hole, time slowed dramatically. On Earth, it sped up slightly due to our planet's gravitational pull. Meanwhile, quantum mechanics painted a very different picture of time. It was a rigid backdrop, the same for everyone. No matter where you were in the universe, time would be the same. It was an absolute. These discrepancies didn't just be an academic curiosity. Reconciling these theories has been one of the driving motivations behind major advances in physics throughout the 20th century and continues to be the holy grail of modern physics. It's why researchers have spent decades searching for the hypothetical particles that make up string theory or those who study loop quantum gravity and other approaches. It's there, amid the contradictions between Einstein's general relativity and quantum mechanics, that the truth about time might lie waiting to be uncovered. That idea was first floated by American physicist John Archibald Wheeler and his student, the late Bryce DeWitt, in the early 1960s. They came up with a way to combine general relativity and quantum mechanics into a single framework. If successful, this would resolve one of the biggest problems in physics. They also stumbled onto something astonishing. Their combined theory eliminated the dimension of time. In Wheeler's words, time is an illusion, only the appearance of things. This apparent paradox can be understood by examining the famous equation E equals mc, which shows that mass and energy are interchangeable. Now imagine compressing this equation to describe the entire universe. You get something like this: h_barg, where h represents Planck's constant, the fundamental unit of action in quantum mechanics. G is Newton's constant, which determines the strength of gravity. And bar, of course, is the antisymmetric tensor representing the metric of spacetime. But here's the kicker. When you manipulate these variables mathematically, the t, the time variable, disappears. In other words, the equation doesn't care about time. It has no place in this particular representation. This apparent disappearance of time puzzled physicists for years. What did it mean? Did this equation somehow reveal a deeper, more fundamental layer of reality? We may not know what time is, according to some of the world's foremost scientists. It might not exist. If that's true, then our entire conception of reality might need a dramatic rethink. Because whatever else we think time might be, it's clear that without it, reality wouldn't work. Or would it? In his book, Reality is Not What You Think, Oxford physicist The Dawn of Modern Physics brought about a revolution in our perception of the universe. No longer were we passive observers of a Newtonian clockwork cosmos. We became travelers who could warp space and time at will. If we wanted to cross the vast expanse of the Milky Way, all we needed was a rocket capable of reaching speeds close to light. The late 20th century was a golden era for astronomy and cosmology. Images of distant nebulas and galaxies revealed a universe in constant expansion. The Big Bang Theory, proposed by Georges Lemaître in 1931, elegantly described how the universe evolved from an extremely hot, dense state into the cosmos we see today. With the addition of Einstein's general relativity, this model of the universe ticked along brilliantly, explaining the motions of celestial bodies and predicting the bending of light around massive objects, gravitational lensing, and the existence of black holes. This period also saw the advent of quantum mechanics, the theory that explains the behavior of matter at the atomic and subatomic level. From this perspective, the behavior of the universe was governed by an entirely different set of rules. Things weren't neat and orderly. They were inherently uncertain and probabilistic. Cats were both dead and alive until observed. Particles could be in two places at once. Reality seemed to be playing by a different set of rules. But there was a bigger problem. These two models of reality appeared incompatible. But the path towards a resolution might be much simpler, according to one provocative idea. It may be that our concepts of time itself are entirely wrong. It was Italian physicist Carlo Rovelli who finally cracked the code. So how does this square with our lived experience? If this is true, then time, at least the way we experience it, isn't a fundamental aspect of reality. So is there a deeper level of reality beneath this one? A level where time doesn't exist? It's too early to say for sure. As humans, we've always been fascinated by time. So what do you think? Is time an illusion? Do let us know in the comments section below.